welcome to the EGB320 Mechatronics Design 2 video presentation. My name is Josh Taylor. I'm in charge of the Mobility Subsystem and Scrum Master. Also within the development team, we have Kosha, Jared, and Jacob, who are responsible for navigation, vision, and collection subsystems respectively. The client, a company called EGB320, has tasked us to develop an entirely self-contained, non-externally operated self-driving collection rover, which is capable of retrieving a simulated sample in the constrained Lunar environment. During the development, we used Scrum. We converted the client specifications into features with designated effort values, where we'd have each set of sprints aimed at different milestones. As seen by the burn down chart, the development team was able to effectively keep on track during the development process. Also during which, we had been given a limited budget of $185. For the final project, as seen by the pie graph of the budget breakdown, the team was able to stay under budget by 88 cents. I will now be presenting the mobility subsystem. Given the client specifications, the robot must be able to maintain the forward velocity of 0.05 meters per second, be able to complete a 360-degree turn without exceeding the 15-centimeter turn radius, push the added weight up an incline, and fit the design within the 15-centimeter cube. The differential drive was selected for the driving mechanism given previous experiences from other work projects. A cardboard mock-up was created for testing to prove the concept. Next, to fulfill these requirements, the development team designed an FBD of a wheel going up an incline. From this, we developed an EOM, rearranged that and plugged it into a MATLAB script using the maximum loads and specs from the wheels. We were able to generate this graph. Wherefrom, using this graph, the development team can plug in several different motors till they found the one with desirable specifications to match client requirements. From this, pulse width modulation was used, and as you can see, the robot can fulfill all mobility requirements and fit within the 15-centimeter cube.
The vision system allows the rover to continuously see and make decisions from what is around it. To be successful, the vision system must have the ability to detect both the objects within the arena as well as the arena boundary. Object detection is done by converting the captured images into the HSV color space before a mask is created for the specified object and a bounding box is drawn. The boundary of the arena is done similarly, with the image captured being converted into the LAB color space, so a mask of the wall can be created, from which the program determines where the wall touches the ground of the arena. The result is a pretty robust vision system, where all necessary objects within the arena are detected with very few false positives and almost no false negatives seen. The boundary vision also works quite well, following the outline of the arena, only having problems when an object obstructs its view, which is fine as the object closer to the robot is more important.
My name is Jacob Rose and I was leading the sample collection management. Mechanically, the system consisted of 2 arms, an axle, a bearing, a servo motor, a connector, and this was all housed by 3 walls. Ultimately, movement was controlled by a servo motor that would turn and rotate the axle and was attached via the connector. The collection process was as follows. The robot drives towards the sample, and when at a set distance away, the arms would open, inviting the sample into the extraction zone. The robot would then stop and close its arms, lifting the sample up the back wall at least 10 mm off the ground to ensure the sample doesn't get contaminated. Theoretically, the robot would then return the sample to the center of the lander, but as you can see, we had some issues traversing the lander. After the first sample collection, the robot would then make its way to a rock, stopping in front of it, and as the robot opens its arms, the hooks on the arms hook under the rock's opening and throws it away. The robot then drives forward and collects the new sample. This process is repeated until all rocks are flipped and samples returned.
The navigation system is the main integration between the other subsystems used in the robot, as it is required to know when the mobility and sample collection systems need to be active based on data received from the vision subsystem. The navigation system must be able to use data from the vision system to navigate through any unknown lunar surface, and accurately collect samples while avoiding obstacles and flipping rocks when required. The code for the navigation system is similar to a bang-bang line falling robot, meaning the robot detects whether the bearing of the object it is prioritizing is to the left or right from the center point of the camera, and turning accordingly depending on whether it wants to be heading towards or away from the object. As seen in this video, the robot can accurately collect a sample and flip a detected rock, although issues with the mobility system on the lander prevent the sample from being fully collected to the center of the lander. This is due to improper integration between the mobility and navigation systems together. This could be improved in future iterations of the product through different factors such as larger wheels or increased power when approaching the lander. The next video shows the robot accurately detecting an obstacle while driving and adjusting its driving course to traverse around the obstacle and check for any samples the obstacle may have been blocking from the camera's line of sight.